Recording started. Cool. All right, good afternoon, everyone. My name is Dominic Leone. I've been a software consultant here at Solution Street for a little less than 2 years now. Always kind of been interested in machine learning, so I figured a nice tech topic would be, would you survive a slasher film? All right, so we're going to take a machine learning approach to this problem. We're going to analyze the characteristics of about 150 slasher film characters. We're going to build a model off those characteristics that, when given new data, we'll be able to make predictions off those characters, whether or not they survived or died. So it makes sense to start with the definition of a slasher film. All right, this comes directly from Wikipedia. So slasher film, a film involving a violent psychopath stalking and murdering a group of people, usually by use of bladed tools. So I think that's fairly straightforward. So what I had done, I watched quite a few movies. I watched 16 films, and I recorded the attributes of all the major players, any significant characters who had more than, let's say, a minute or two of screen time. All right, I recorded a few attributes as well as whether they survived or died. But these are the films I watched. Originally, I wanted to do a bunch of random films, but it proved difficult to find them, to get access to them legally. So most of these were on like Netflix or Hulu or whatnot. But there's a nice range here. We go from the 70s on up to last year. A few more popular ones: Scream, Friday the 13th. A couple less popular ones: Torso, House on Sorority Row, Hell High. Some really bad films in here, but I trudged through it. I didn't watch Halloween. I should have. I know that was considered one of the first slasher films, but Torso might actually be one of the first, because Halloween was late 70s. These were the characteristics I recorded about each character. So we looked at gender. Most of the time it was male and female. Only in one film was there an other. Ethnicity, whether or not that person was a main character. Age range, hair color, stereotype, occupation, sexual proclivity, whether the character got naked in the film, drug and alcohol usage, and mental and physical performance under duress. So just a couple quick notes here. Some poor examples of mental and physical performance under duress: inability to climb a ladder, right? Running up the stairs or into the basement when the killer's in the house happens way too often. Same thing, trips while running, pretty much every single film. For some reason, a lot of police officers like to hide the fact that people are getting murdered from the townsfolk too, so no one ever knows for some reason. Stereotype as well, just want to have a note here. So real human beings, we can't necessarily put into these boxes of stereotypes, but movie characters, we can, right? Film directors and screenwriters only have 15 minutes to 2 hours or so to really build this connection between the audience and the characters. So a lot of times they'll exaggerate stereotypes. For instance, a cheerleader. She might, pretty much the whole movie she's wearing her cheerleader outfit, whether she's walking around school, whether she's at home eating dinner. Same thing with quote unquote jocks, right? They're always wearing their varsity jackets. Nerds always have to have glasses, right? So they exaggerate these stereotypes so you can sort of build a connection and understand who they really are. But real people, we can't necessarily do that. Just want to make sure I'm not offending anybody. Doing my best here. And along with those attributes, I also recorded whether or not they survived or died, which leads us into the next slide. How we're doing this. We're using something called supervised learning, where we basically have the data, which we'll call features, and we have the outcome, which we'll call labels. We're going to use this information to build a model that will take in unseen data, so unlabeled attributes, and put a label on there, whether or not they survived or died. This is a bit different from unsupervised learning, where we don't have the labels. We just have a bunch of attributes, right? So we're clustering data together. An example would be a recommendation engine. So if user 1 likes movies A, B, and C, user 2 likes movies A and B, there's a good chance user 2 is going to like movie C as well. All right, so we're using supervised learning because we have the features and we have the labels. Couple things before we start making predictions. So we have our data, but we need to do a few things with it first. When I took all the notes and recorded in the spreadsheet, I pretty much just wrote strings down. So hair color, I wrote down blonde, brown, ethnicity, Caucasian, African American. But we need to put this in a format that our model is going to understand. So a first pass implementation, you might think integers. For instance, we have hair color. We have blonde, black, red, green, or bald. Green, I don't know why green is in there, but we can map these to 0, 1, 2, 3, or 4 respectively. But there's a problem with this. right? We've essentially introduced order or a sense of ranking where there is none. Meaning, if we went by these values here, we're saying bald is greater than green, which is greater than red, which is greater than black, which is greater than blonde. Which is, I mean, true for the bald, but not necessarily true in general. Right, so we basically, our data is nominal, so no sense of ordering, so we can't just assign a different number to these. If there was a sense of ordering, let's say strength, maybe you'd rank from 0 to 5, we can leave that in. We wouldn't have to do anything with that data, okay? So what we're gonna do, we're gonna one-hot encode the data. All right, what this means, we create a new binary characteristic for each value that an attribute can take on. So we have hair color, right? Originally, that was just one attribute per character, right? We're now expanding that into, let's say, 5 attributes. It would be hair color blonde, hair color brown, hair color red. And we put a 1 wherever the person's hair color is. Let's say they're blonde. So hair color blonde is a 1, whereas hair color red, 0, hair color bald, 0, etc. This creates a bit of a sparse array. We could reduce dimensionality using things like PCA, which is principal components analysis, or SVD, singular value decomp, but we're not really going to get too deeply into some of these topics. What happened here was I started with 11 attributes. My array per character ended up being about 68 attributes with all the different stereotypes and the different occupations. And just to kind of to show this here, so these are 3 characters. Let's say they have blonde hair, red hair, brown hair. We've expanded this. So hair blonde for the first person is 1, whereas it's a 0 for all the other hair colors. Second person, hair color red is a 1, everything else is 0, etc. Okay, this makes sense so far? One other thing we need to do with our data, we need to split it. So we need to split this into a training and testing split. Basically, we're using the training to continuously update our model, and then we check the accuracy using our testing data. Right, so typical split, 70% training, 30% testing. So you might ask, Dom, why don't we use 100% of the data, right, for training and testing? It's a very good question, everybody. We want our model to generalize well to unseen data. If we're using all the data that we have, really, we're training our model to work exactly on that data. And there could be some noise in that data. There could be a lot of errors in that data. All right, so we're really training our model to know those errors as well, and we don't want that. So this leads to overfitting of the data, which is called high variance. So we might not achieve great results on unseen data. And this is the opposite of underfitting or high bias, where we just don't train the model well enough and it just doesn't perform well at all. What we want to do, we want to try to find this bias variance trade-off. So we want to find a balance between underfitting and overfitting. Okay, so at this point, we have our data. We've split it. We've also one-hot encoded everything. Now things are going to get a bit mathy. Okay, so just a warning. I'm going to try to be as light on this as possible and try to be as clear too. But we want to create a function that when given the attributes of a character, we output a probability. And then based on that probability, we can use a threshold. If the probability is, let's say, less than 0.5, we say it's a 0, they died. If it's 0.5 or greater, 1, they survived. So there's a couple different parts to our function. We have our hypothesis, and we have the activation function. All right, so let's go through this slowly. Hypothesis is basically weight 1 times x1 plus weight 2 times x2, all the way up to weight n times xn plus b, or in matrix notation, wx plus b. Our x values are the attributes, which are, in our data set, 1s or 0s. Ethnicity, Caucasian, 1. Ethnicity, African American, 0. Right? And then the weights are the values that we're going to need to adjust to make our model accurate. Essentially what we do, we're building a decision boundary in a multidimensional space. So on one side, those that survived, the other side, those that were not so lucky. One problem with this hypothesis function, however, is that we want a probability, but we can output a value anywhere from negative infinity to positive infinity, and we don't want to do that. That's where this activation function comes in. All right, it looks a little scary, but it's not too bad. I'm going to show on the next slide what it really looks like, but it's 1 over 1 plus e to the negative x. All right, so this basically squashes our value from between 0 and 1. If we basically, ultimately, we're wrapping the hypothesis with this activation function, and it ends up looking like this. 1 over 1 plus e to the negative weight 1 times x1 plus weight 2 times x2, all the way up to the bias. And then at that point, we're given a float, and we can use the threshold to output a 1 or a 0. And this is what our sigmoid function looks like, which is that 1 over 1 plus e to the negative x. All right, so you notice as we approach infinity, it begins to approach 1. As we approach negative infinity, it begins to approach 0, but never reaches. Okay? Everyone's with me so far? It's going to get worse. Okay. Oh boy. So, how do we adjust the weights to get the model really accurate, right? First thing we need to do, we need to understand the cost of our function, or really how accurate the function is given the current state, given the weights. We're going to be using this, cross-entropy log loss function. It looks scary, but it's not. Trust me. There's only two variables here. There's y, which is the actual value, y hat, which is the predicted value, which is what we get from the logistic regression classifier. All right, so forget the summation in the beginning. If we just wanted to calculate the error based on one character, we'd simply plug in the values. Right, so if our actual value is 1, we're only using the first part of the function. Because if you notice, if we put a 1 into the second part, we're zeroing it out. Same thing, if our actual value is 0 for a character, we're only using the second part of the function because we zero out the first part. And a correct prediction of 1, if you're putting it into the first part of the function, is going to give you a 0 of an error because natural log of 1 is 0. Okay? If you're completely wrong and you predicted a 0, you're going to return negative infinity because the natural log of 0 is negative infinity. And then a similar thing happens in the second part for the 0. So I'm not so concerned whether or not you understand entirely what this means, but basically what we're saying, the more wrong we are, the greater our cost. So at any point, we can kind of see how well we're doing based on these predictions, and we can calculate this log loss. Still with me so far? It's going to get worse. All right. Gradient descent. So we talked about the cost, right? And we talked about how to make the predictions, but how do we optimize those weights inside the logistic regression classifier to actually give us real responses here? So we're going to use something called gradient descent. And this is at a very high level. We take the derivative of the cost function with respect to the weights, plug in values. Okay, we get these deltas. We multiply the deltas by a small learning rate, and we subtract from the current weights. And that'll be a bit more concrete on the next slide. But what I wanted to show here is that we can sort of graph our cost function with respect to the weights over here, right? Because when we take the derivative of the cost function, we're finding the rate of change. So we know in what direction our cost is going to get worse. Therefore, we know what direction our cost is going to get better. It's going to get lower. Therefore, we can adjust the weights accordingly. And this learning step is going to be very important, the learning rate that we multiply by, because we could overshoot the global minimum. If the learning rate is too high, we can end up over here and we can go back and forth, penduluming, is that a word? Going back and forth over here. Or if the learning rate is too small, we might never even reach that minimum. The other thing that's nice, let me step back for a second, about the cross-entropy function is that by using the logs, we get somewhat of a smooth function. Okay, it's also monotonic, meaning that it's always decreasing or always increasing, meaning there is a global minimum that we should be able to find. We can still get stuck in some kind of peaks and whatnot, but we should be able to find that global minimum. For the cross-entropy cost, derivative is actually pretty simple. Considering, right? So it's y, your actual value, minus your predicted value, times your attribute. And then you just take the mean of that. So that essentially gives you a delta, and then you have that delta multiplied by the small learning rate, subtracted from the existing weight. So more concretely here, for one attribute and one character, we subtract the predicted value, which is that float between 0 and 1, right, from the logistic regression classifier. So let's say we said 0.6. So 0.6 means there's a good chance of survival, and their actual value is 1. So it's literally 1 minus 0.6, 0.4, and then you multiply by each of the individual attributes. Okay, so for the first, ethnicity Caucasian, maybe it's a 0. Next one, ethnicity African American, 1. And you take the mean of this, that gives you a delta, multiply by a small learning rate, and subtract from that weight. And that's how you make the optimizations. So if we could just step back for 1 sec. Again, that learning rate is super important because we can keep going back and forth here, or it might be too small where we never hit this minimum. Must be done simultaneously too. So we go through a batch of, let's say, 1 character, 10 characters, 20, whatever we chose there. And we want to calculate all the deltas for each of the weights before making any adjustments. Okay, so we can't calculate the delta for the first weight then make that adjustment to the weight, and then calculate the delta for the second weight, then make that adjustment, then calculate the third weight. Because again, our predictions, where is it back here? Yeah, well, our predictions rely on this y hat value, the calculated value. So anytime you make a change to the weight, you're going to be changing your predicted value. So basically, you want to use the same predicted value through the batch. All right, so you go through a batch of 10, you update all of 68 weights, then you go to the next one, update the 68 weights at the end of it, et cetera, et cetera. We can have multiple epochs, so we're going to want to train this so that it performs well. So we can go over it, let's say, 1,000 times, 10,000 times, whatever we need to do. And the learning rate, again, which we talked about there. So those are kind of two hyperparameters we can tweak with gradient descent. All right, so I'm going to stop here. Does anyone have any questions on what we've gone over? I know it's a bit complex. I'm trying to sort of glaze over the math a bit. Just want you to have a basic understanding of what we're doing. Yes, sir.
Yeah. So, I guess this is a much more basic question. Did you do this by starting out, it's just guessing randomly, and then you're telling it right or wrong, and then just
yes, essentially. I failed to mention that. I'm sorry. The weights, you start with a bunch of small random values. So initially, your predictor, your logistic regression classifier, is going to be awful because it doesn't know anything. And when we take a look at some results, you'll see that. So we start with a bunch of small random weights, and then we iteratively adjust them so that our model gets better and better. Good question, though. Nice. Anybody else? All right, we're almost done with the math. Okay, accuracy, this is it. So accuracy is basically the number of correct predictions divided by the number of total predictions. So we're going to use this to sort of see how well our model's performing. We could reuse the log loss function over our data set, but I felt like accuracy was a bit of a clearer measure. There's other things we can do precision, we can look at recall, we can look at F1 scores, but accuracy just seems like the easiest one to understand. So now, question for you folks. If we only consider that we have two target values of equal probability, what kind of accuracy do we want to reach if we wanted to do better than random guessing? Yes, or 50.000001 I would have accepted as well. Okay. Now, considering, I'm telling you that 70% of our characters die, right? So if we know that, without even using machines, I like the thumbs up, without even using machine learning, how do we create a model that performs better than 51%?
It guess they die 70% of the time. Or 70%.
Yeah. So just go through a data set, say everyone died, and you're at 70% accuracy. So we want our machine learning classifier to be better than that. Okay. And in fact, this is one set of results, and we're going to run through some real-time results, and we'll look at them and see what happens. But yeah, for the most part, we are able to do better. Right? This depends on what you end up when you split the data between training and testing. So for example, my initial accuracy, a bunch of random weights, 23%. I said everyone died, 80%. Post-training accuracy, 87%.
Question.
You in the back.
Yeah. Your initial accuracy is significantly lower than 50%. Is there a reason for that?
It's completely random. Okay. So if I were to run it again, I might get 40%. I might get 60%. You just don't know.
Well, maybe it's because there's a more than 50% chance of dying.
Right. So that could affect it too.
Oh, okay, yeah. Like if there was 50% dying, probably.
Yeah, probably, possibly. Well, the weights are sort of random all over the place. But yeah. And then if I ran it over the full set, really no reason to, but just because. Initial accuracy 33%, all dead 70%, post-training accuracy was 85%. So we were able to beat just saying everyone died. Let's discuss what those weights really mean. So if we go back to that logistic regression classifier, remember we had that hypothesis, that long function W1x1 plus W2x2 plus W3x3. Basically, we're shifting these in directions. So the more positive weight kind of pushes you towards survival, the more negative weight pushes you towards death. All right, and this makes sense here. So some of the more positive weights I noticed, lawful good stereotype, doctor, I guess because slashers are going to need a doctor at some point in their lives. Protective, good under duress. Okay, so these are kind of good qualities that you as the viewing audience really can try to hopefully relate to, right? Most negative weights. So we have poor under duress. That makes sense because you're making bad decisions. You're not going to live, right? Drugs. If you take drugs, you're inhibited and you're not going to make good decisions either. Sexual stereotype, comedian stereotype. So really, yeah, if you're in the movie just for eye candy, no one cares if you survive or die, really. So that's typically why they do that. I've noticed with comedians, sometimes they're a bit overbearing. So you as the audience will kind of cheer when they get killed, right? So that could be why that happened there. Another interesting trend. So as you become more sexually active, your chances of survival diminish. just letting you know here. Yeah, me too. So, all right. What's important to note here is that these values could change entirely based on your training and testing split. Because I don't have a lot of data, right? Taking a small sample of that already small data set, I'm not really getting a clear picture of the population. I'm really not getting a good sample. For instance, let's say out of the 150 characters I had, I don't know, 5 people with red hair. If I take a training set that has nobody with red hair, my model doesn't know what to do with that, right? So it just kind of puts in random values for the weights, and then we just really don't know what to do with our red hair. And this could happen to a bunch of attributes. So having more data is always better. It always helps with this issue. And unfortunately, 150 characters for 68 attributes is not a good ratio. Okay, I mean, we were still able to get some sort of accuracy here, but wasn't too great. So let's run this in real time, and we'll see some differences. We'll look at some weights too. Where are you? I had written this in Scala, all right, and this ended up being about 250 or so lines of code. On the right, on the left, we have our Scala worksheet, and on the right is going to give us some results. So we'll take a peek. After stochastic gradient descent, which is batch gradient descent. I did worse, but I still did better than the initial accuracy. Again, this is because I don't have a large data set, and probably my training set just didn't have good data in it. But somehow, if we ran it over the full set, so the same weight from here over here, we got 80%. So we did better. All right. So we're basically always improving off of the initial accuracy, not always improving on the all dead, because I just don't have a lot of data. I'm sure if I had more data, my results would be a bit more predictable. Right now, as we scroll down, yeah, this one was actually pretty good. Where did it go? Yeah, so on the test set, I was able to get 90% accurate. All right, so at this point, let's look at some of the weights that this has generated. All right, so I would say anything, can we make this bigger? Nope, that doesn't do it. View, zoom. I would say anything maybe less than 0.5 or greater than 0.5 or that range really has an effect on our model, right? So gender unknown didn't have much of an effect. Female, so we have a fairly negative weight here, and that's because I'm willing to bet most of my data set female. And being that 70% die, that's kind of indicated in this weight here. Age range, looks like 23 through 30 is a little safer than 16 through 22. 0 to 15, I guess because they don't do much with younger people, and there's probably not too many in here. I'm trying to be cautious with my words. Older people, okay, let's see. Ethnicity, I didn't have a lot. Even though I watched 16 films, these are the only 2 ethnicities I saw. So I didn't get a really good range here, unfortunately. But yeah, you can make your assumptions from that. If we look at the sexual proclivity so this makes sense. Inactive pushes you towards survival. Active, not so lucky. And then extremely active, I probably didn't have a lot of characters who were extremely active. And by extremely active, I meant they had multiple partners in the film. So I probably didn't see a lot of them. Nudity, you don't want to get naked in the film, right? So that's negative. Stereotype unknown. So if I wasn't able to really give you a stereotype, that means you were significant enough to be in the movie for a minute or two, but you really weren't significant enough to have any defining characteristics. So there's no reason to keep them around. Stoner, yeah, you don't want to be a stoner. Geek seems like you're safe, guys. All right, so here, stereotype sexual, huge negative effect on that. So you don't want to be in the movie just for eye candy. Killers do not like that. Stereotype creep, if people don't like you, obviously you're not going to survive here. Crazy, same thing. Jerk, same thing. These are huge negative influences here. Lawful good, huge positive influence. So these are a lot of times police officers, doctors, just friends that are very helpful. Stereotype drunk for some reason, nope, negative. So you kind of get the picture here. Stereotype doctor, again, a huge positive influence. So the weights are shifted accordingly. And then if we get towards the end, where are we? Hair color didn't seem to really affect, bald people don't live. I was hoping that wouldn't happen. Old people, here we go. No one in here is old. Drugs, again, negative effect. So what I saw had a huge effect was this here, the performance under duress. And really, I mean, that makes a lot of sense. If you're making smart decisions, you're going to survive. You make some poor, some good decisions. It doesn't really do much. Poor decisions, you're not going to survive. And if you're the main character of your own film, good chance you're going to survive too. All right. A lot of people really fell under this duress average, honestly. For instance, if you were to watch Scream, a lot of people have seen Scream here. Main character, Sidney Prescott, she does a lot of bad things, but she does a lot of good things too. She doesn't get naked, she almost does. But she drinks, she has sex in the film, she runs up the stairs when she shouldn't. But in the end, she came through in the end with just making smart decisions to survive. So she was more like duress average.
She has sex, but she doesn't get naked.
Exactly, yes. Well, I'm sure she did get naked, but we did not see it. Yes. We did not see that part. And now I'd like to show you this same code in Python. If I were to remove all the comments, this is 17 lines of code. Whereas in Scala, I had to write about 200 because I built it from the ground up, right? I built the classifier, I built the stochastic gradient descent, I built the one-hot encoder, but everything is in a library. So my recommendation, if any of you are interested in machine learning, start with Python and start with this library called sklearn. It abstracts away all the complicated parts that we talked about today, all the math functions and whatnot, and really just allows you to say what you want to do and do it. So we're loading in the data using pandas, which is another library. We're one-hot encoding certain characteristics, whereas main character, drugs, and nudity were already binary. We split the data. We classify it, so we're training the data with that dot fit, and then we're predicting on the test data. And I received similar results using Python as I did with Scala. So if anyone's really interested in machine learning, use sklearn. There are other libraries as well. There's TensorFlow, there's Keras, there's a couple others, but those you have to know a bit more of the math side. So I would really start with this and then kind of start picking up the lower level, the math. Yes, sir?
I would also suggest, if you're going to start machine learning on Python, you might want to look at Plotly library because that's a good charting tool.
Okay.
That you can visualize for big data finding.
Okay. What is it called?
Plotly.
Blockly?
Yeah.
Gotcha. Yeah, there's another one I've used in the past called PyCharts. I didn't load anything in here, but yeah, thank you for the recommendation. And if anyone wants to get into machine learning, needs a little bit of help, I'm here for you too. So just let me know. I can kind of come over, just show you the ropes a bit on how to use sklearn. Okay, where were we?
Load all of the characteristics of all the employees here.
I did. Originally, I wanted to build like an on-the-fly classifier and say, hey, you, give me some of your characteristics, but I'm not going to ask what you define yourself as a stereotype occupation. I don't want to ask people's ages. if you're going to get naked, your sexual proclivity. So it seemed like something we didn't want to go down. We didn't want to go down that road. Yeah. Yeah, you know. So let's talk about some improvements. Right? Is the data varied enough? Did I grab data from a broad enough range of decades or cultures? Maybe it's too varied. Perhaps honing in on specific decades and cultures would yield more predictable results. I mean, I'm willing to bet if I'm sure I could find 30 campy slasher films from the 80s, and they probably fit the same stereotype, each one, and we could probably get like 95% accuracy on those characters because they all fit the same molds. Whereas going over a broad range of 70s Italian films to 2010 jump scare films, they're different, right? Errors in the data. Am I a reliable source to record the information? So did I record everything correctly? Probably not. I mean, I watch the films, and then usually afterwards I start recording information about the people. And sometimes, maybe I entered a 1 where I should have entered a 0. And a lot of films, older films, get washed out with the colors. So I couldn't tell if someone had blonde hair, red hair, brown hair, or black hair sometimes. Yeah, crazy. I also had to use my judgment on insufficient information about characters. So sometimes I had to guess their age range or stereotype or other things of that nature, because there just wasn't enough information, but they were significant enough for me to want to record them. More data. Only collected results from 16 films, right? Ideally, I would have watched more so I could have gotten a broader sample of data. And I only collected 11 different data points per person too. So I could have recorded other things, height, colors that they wear, if they ate a pickle in the film. I don't know, just other data points I could have used, and just didn't. We could have found some latent attributes there that may have been predictors, and we don't know. We also could have used different models, right? So we used the logistic regression classifier, but we could have used neural networks, which are really just a whole bunch of logistic regression classifiers combined in really interesting ways. We could have used decision trees, which work almost like if and then statements. There's a naive Bayes classifier. There's AdaBoost. There's so many that we could have used, but I opted to use the logistic regression classifier. So some key takeaways. Machine learning is a mostly automated process that uses existing data to build a model that predicts information about unseen data. This is not about writing conditionals using domain knowledge. I'm sure any one of us with any kind of knowledge of survival of slasher films could have said, all right, if the age range between 22 and 30, gets naked in film, has sex, died, else survived, or something a bit more complex than that. But you could have written that, and you could have done fairly well. But the beauty with machine learning is that it doesn't care about the domain knowledge. It doesn't care what kind of data you're feeding it, right? We're just feeding the model data and letting it really determine how to predict those outcomes. So just to recap as well, logistic regression was a classifier that predicts outcomes given numerical inputs. We had that hypothesis that W1x1 plus W2x2 wrapped by the activation function, which was that sigmoid function that scaled it between 0 and 1. And then we were able to generate a probability. Then we had the threshold to say, all right, died or survived. Gradient descent was what optimized the weights. By pushing values towards that global minimum, we had the two formulas. We had the cost function, which is that scary looking log thing. And then we had the derivative of the cost function with respect to the weights, which allowed us to actually perform those optimizations on the weights. All right, so I hope that this talk has given you a bit more insight as to what machine learning really is. So it's not this just magic black box that you throw numbers into and outcomes, you get predictions. I also hope that you've learned a bit more about what your chances of survival will be if you find yourself in a slasher film. Questions? I went through that quickly. I'm so sorry, but questions on anything?
So if it turns out that the attributes of a character actually have nothing to do with whether or not they survive, do you think your machine would make similar accurate, like predictions with similar accuracy? Or do you think we would see it match more closely to just percentages?
I'm sorry, say that again. I didn't quite understand.
Let's say the data that you're feeding it actually has nothing to do with the outcome. Yeah,
right.
Like the pickle. Yeah,
so then you'll ideally, if we had a huge enough data set, you would end up being close to 0 for that. It wouldn't have an effect, positive or negative.
Okay.
So really, I mean, I'm sure a lot of those attributes didn't really have much of an effect. Like, I don't know. I mean, I don't know. Maybe hair color doesn't have an effect. Maybe it does. But some of those probably didn't. And yeah, the weight would probably start minimizing itself to 0 eventually over enough epochs. So you train your data set 1,000 times, 10,000 times, it would improve each time, depending on your learning rate. If your learning rate is too high, it's going to overshoot the minimum. And if it's too small, it's never going to get to that minimum.
What does data look like?
Yeah, let's take a peek at that. Yeah, it's just a spreadsheet. Is this it? Yeah, so spoilers, all right? Let me just, actually, yeah, that's pretty big. So yeah, I mean, it's just a spreadsheet. I wrote, these didn't matter. I just recorded these just so I knew. But I started here. So gender, female or male, or other, age range, ethnicity, sexual proclivity, nudity, occupation. So these are literally strings. So that's why we have to pre-process the data to turn them into numbers. And then at the end, we have whether they survived or died. And you can see a ton of zeros. Yeah, I think all in all, it ended up being like 69.9% of people don't survive these films. But they're significant characters, right? There's always random people walking in the background that, of course, have nothing to do with the film. And yeah, these are just more movies, more characters, etc.
Which movie was your favorite?
Oh boy, out of all of these, I really like Torso. Torso was a early 70s flick, one of the first slasher films, and it's just low quality, low budget. I don't know, something about it. Very gory. Those are the kind of movies I appreciate. I swear I'm not weird. Sleepaway Camp's pretty good too. But some of the bad ones, Slaughter Hotel, awful. Hell High was pretty bad. House on Sorority Row, the original, wasn't good. So good mixed with bad. Mostly like average films.
Sorry if this isn't a great question,
No.
but so it seems like there's a lot of work to define attributes and to collect your data. Is that typically the case?
Yes.
In terms of
Yeah, I mean, honestly, this Python script, did I close it? No. This Python script took me 10 minutes. Recording the data took 16 times 2 hours, 30, 40 hours to record the data. So that's a huge part of it.
defining your attributes is,
Yeah.
I mean, a lot.
Yeah, so honestly, 90% of the battle is collecting enough data and good data. And then throwing it into here was nothing.
And where does the term one hot come from?
I'm not quite sure, actually. I mean, I guess it's one hot. Oh, because with binary characteristics, if it's hot, it's a 1. If it's not, it's a 0. So it's so you're basically converting all the values that your attribute could take on into binary, 1 or 0. Yeah. Any other questions from anybody? No one. Cool. Thank you so much, everyone.